Hi everyone, and welcome to our video on solving trigonometric equations that involve special angles. So what do we mean by special angles is just the angle that is in the trig function. Let me put it in parentheses already way down here. So on number one, that's 3 theta. So what we mean by special is just that it's just not x or not theta. So not special, we'll say, is something like sine of theta equals 1/2. So just, or sine of x equals 1/2. So just a single letter, that's all that's involved. Whereas these are special down here because it's not a single letter as the angle, and it might help to put those in parentheses. Let's do it there too. And even one more, it's already down scrolled like that. Okay, so there's the angle's got something special going on. However, what's nice about them is that there's only a single trig function. So it is similar to our introductory trig equations where we had a single trig function and then we worked with it. These ones are just going to take a little extra time because of that special angle. Now, one thing to point out for future problems, something like this. So this has a special angle in it, but there's another trig function involved that has a regular angle in it. So we usually do these differently. So the special angle style problems that we're currently doing is when it's a single trig function and a special angle. All right, let's see how we do this. Okay, so here's all of the steps that we'll break down. Let's find all solutions of each equation and then find the solutions in the interval 0 to 2 pi. All right, well, to do that, this first one, we should divide by 2 immediately. So our goal is still to get the trig function all by itself. So we want to divide by 2. And that gives us cosine of 3 theta is equal to radical 3 over 2. And then it's right back to the unit circle where we're saying, oh, that radical 3 over 2 represents an x coordinate. Positive radical 3 over 2 is right here at pi sixth. And then down in quadrant 4 at 11 pi sixth. So that means this angle, so the 3 theta, would equal pi sixth, and then we'll go ahead and add 2 pi k, comma, the 11 pi sixth plus 2 pi k, where k is an integer and just letting us know it keeps going around the unit circle forever. So these answers keep getting repeated as coterminal angles. All right, and then this is where we would have ended if it was as basic as possible with just the angle theta, but we had 3 theta. So usually at this point, it's best to get a common denominator with our answers. So currently there's a 1 under there. So let's multiply each of these by 6. So we have a common denominator. So I still have 3 theta, but 6 times 2 is 12. And I'm going to go ahead and combine it into a single fraction in this same step also. So my first answer now looks like this, pi plus 12 pi k over 6. My second answer looks like this, 11 pi plus 12 pi k over 6. Now, again, I want theta all by itself. Well, to get theta all by itself from here, we should multiply everything by 1/3. Okay, so we've got, let me just do it like that. Let me put parentheses. Okay, so everything's getting multiplied by 1/3, so the 2 answers and then the 3 theta, and that way I would have just theta. So just like any solve, any problem, they want just the letter eventually, and so that's what we're doing in this step. Okay, and so in my numerators, I have pi plus 12 pi k over 3 times 6 is 18, and then comma, 11 pi plus 12 pi k, and then 3 times 6 is 18. Okay, so it looks like this. Now that we have it, so this is all solutions. So I'm going to cloud it. They might want it, and I did right. This was part A up there, so all solutions. Okay, however, usually they want B. That's usually more important for them in these problems. So it says find the solutions in the interval 0 to 2 pi. Well, this is where we do let k equal the values of 0, 1, and so forth. So for B, we're going to let k equal 0, 1, 2, and however many we might need to do. Now, what I usually do in these problems, though, is I focus on that 12 pi. So I focus on whatever's attached to the k. And then, so k is going to turn into 0 and turn into 1 and turn into whatever. And from there, we don't really have to show plugging those in. What I highlighted in purple is how we're going to count with the numerator. Okay, so what I mean by that, so when we do let k equal 0, we would have theta is equal to, so if we do let k equal 0, let me highlight it. So if we let that k equal 0, that means that second term is gone in the numerator. That would turn to 0. And so we would have pi 18ths, comma, 11 pi 18ths. Okay, and then now we would be letting k equal 1, but really now it is just counting by what's in the purple, by adding it to this initial pi. So we should go pi plus 12 pi, and that would be 13 pi. And then still over 18. And then for the second answer, we would again just say, well, let's add a 12 pi. We're going to count by 12 pi's added to this answer. So that would be 23 pi over 18. Okay, and I'm just keeping in things in order, but look at this. Okay, so there was an addition of 12 pi to the numerator. I'm just going to write it like that, plus 12 pi over something. And this one also was plus 12 pi to the numerator. So I'm just going to keep that pattern going. Okay, so this 13 pi, if I add another 12 pi to that numerator, that would be 25 pi over 18. And if I do it again to this one, that would be 35 pi over 18. Okay, so I'm just counting. So that would have been if I did let k equal 2. And then let's do it one more time just to see it. So this 25 pi over 18, if I did add 12 pi to the numerator, it would be 37 pi over 18. But 37 divided by 18 is bigger than 2, and then the pi is still attached. Bigger than 2 pi, and that's not on the interval that they said. So they said between 0 and 2 pi. So that means this is no longer an answer, and so we're done with our problem now. So this is the final answer for step B. All right there. Okay, so again, that in the purple is all I'm doing to try to avoid just plugging in and doing a lot of little minor arithmetic. The pattern continues. And notice that even if you look at the pattern a little differently, like if we look at these two, notice the numerators are 10 apart. And then if we look at these two, the numerators are 10 apart. And if we look at these two, the numerators are 10 apart. So there's patterns that we can use to help us check our answers as well. Okay, and like any equation, if we really want to make sure it's good, I'm going to go all the way back to the start. Okay, so I'm going to check. Now, I'm going to choose a random one. If we checked all of them, it could take some time, but I'm just choosing the third one there. So if we check that, I don't have much room to check it. I think I'll erase this and we'll do number 2 in a different video. But let me put that in purple to check over here. So I would have 3 times 13 pi 18ths. And then I want to see, does that equal radical 3? Remember, you always check in the original equation, so not after a couple steps, just always in the initial given. Okay, and then we would say, oh, 3 and 18 here would reduce. So we would have 2 cosine of 13 pi. 18 divided by 3 is 6. And then again, we're seeing, all right, does this work? Well, 13 pi over 6 does put us back in quadrant 1. So this is 2 times cosine of 13 pi 6, which becomes 2 times radical 3 over 2. And then yes, that is true. Okay, so that one definitely works. Now again, all of them would. If we have tons of time, we could check them all. But those are our final answers. Okay, so let's put a pause on this. We'll do number 2 in another video. Thanks for watching. If you have questions, please let me know.